we're very happy to have Anna Keselman from KITP. And she's gonna tell us about valence bond and gapless liquid states in triangular lattice SU4 antiferromagnets. Anna, go ahead.
Hi, yes, thank you so much. Yeah, so I would like to tell you about essentially ground states. I will be talking about ground states of strongly interacting systems. And more specifically, I would like to talk about systems where the local degrees of freedom are fourfold degenerate, and where this could give rise to an SU4 symmetry or an approximate SU4 symmetry of the model. So to be a bit more specific, the kind of systems I would like to consider are, for example, cold atom systems, where it was shown that alkaline Earth Fermi gases, for example, could be described by various SUN models due to their nuclear spin. In electronic systems, we could have, in addition to the spin degree of freedom, another degree of freedom, like the orbital degree of freedom in transition metal compounds, for example, where again, due to this both spin and orbital degeneracy, we could have 4 degenerate states on each side. And of course, more recently, there was a lot of experimental progress on various twisted heterostructures, which give rise to Marais superlattices, where there is an additional valley degree of freedom. And this, again, could give rise to 4 degenerate states, which are the spin and valley degrees of freedom. So again, more specifically, I would like to discuss SU4 spin systems. And similarly to the SU2 case, I want to think about starting from the Hubbard models, so where I have just some 4 flavors of fermions. And the 4 flavors are now the different spin and valley degrees of freedom, for example, which are hopping on some lattice. And then I would like to put on Hubbard U term, so just strong on-site interaction. And then consider the limit of large U and some integer filling. And note that in this case, compared to the SU2, for example, I could have different fillings of my fermions, and this would, in the spin language, correspond to different representations of the SU4 group. So again, going to the Mott regime, I essentially get kind of an SU4 antiferromagnetic Heisenberg model, where I can write my spin operators now, the TABs, simply in this following way, in terms of the local fermions, C dagger A, C, B, where A and B are the different flavors. So to be a bit more explicit maybe about this model, you can see that I write it here in terms of this 16 operators, essentially. Now, it's important to keep in mind that only 15 of those are actually linearly independent, and those are the 15 generators of the SU4 group. And it's really, I mean, it's kind of easy to see that this model is really like the SU4 equivalent of the SU2 Heisenberg model that we know, where I just write, I could write the S.S operators as S plus S minus, and the S plus S minus are essentially my TABs, except that now I can go between 4 different flavors and not just between the 2 spins. Now, again, thinking of this SU4 in terms of the spin and valley degrees of freedom, I could also write my the spin operators in the following way, kind of explicitly in terms of their action on the spin and valley degrees of freedom. And this is kind of starting from the SU2 cross SU2 limit of the Kugel and Chomsky model, where kind of a specific choice of the coefficients can give me a larger SU4 symmetric point. And here again, we can see that this 15 generators of the SU4 could be obtained from the 3 kind of actual spin degrees of freedom, 3 Valley, and then 9 operators which mix the spin and Valley degrees of freedom. So I would like to discuss understand the phases that this model can have, more specifically on a triangular lattice. And I would like to consider 2 different cases of 2 different fillings. So we'll start with a case of half filling, where we put basically, we start from 2 fermions per side. And in this case, I would like to show that there is we believe that there is a description in terms of a good description of the low energy physics in terms of dimers, and that the resulting ground state is presumably a valence-bond state. And this is a work that was done with Lucille Savary, now in Lyon, and Leon Valence from KTU. And then in the second part of the talk, I would like to address the case of quarter filling, but I'll leave this for later. Okay, so in the case of half filling, we're essentially talking about the 6-dimensional representation of AC4, and the way we can see it is the following. So we think of half filling, again, corresponds to putting 2 particles per side. So if we have 4 degenerate states, we have to choose two out of these 4 states in which we put the fermion, and there are 6 possible ways of doing this, which I could label in the following way. So this is my local Hilbert space I'm starting from. And now to understand what kind of phases this system could host, we could start in a similar fashion, or we could use our experience from SU2 spins and try and understand first what are the classical ground states of the system. And I won't go here through the details. It's a bit just complicated algebra, which involves mapping this SU4 spins to essentially SO6 degrees of freedom. But I'll just state the final result. And what we find is that if we look at the classical limit, which essentially corresponds to looking at the product at the variational wave function, which is a product wave function, we find the state which is very similar to the 120-degree order state for the SU2 spins. Again, it's a very large degenerate manifold that is with a lot of states that are related to each other with SU4 rotations. But for example, one representative state you could think of is if you kind of put the fermions in each at each site into a Valley singlet, and then you only remain with a spin degree of freedom, which now can actually order in a regular 120-degree order. And then that state could be kind of related to the rest of the degenerate manifold by SU4 rotations. So kind of knowing the classical ground state, we could try and understand whether this is also the ground state in the quantum limit. And we can do this numerically using DMRG. So here we're considering finite cylinders, and to probe whether this long-range magnetic or SU4 magnetic order is present in the quantum limit, we essentially put some pinning fields at the boundaries to facilitate the formation of the long-range order, and then probe the expectation values of the spins in the bulk. So this is kind of probing the susceptibility of the system to the magnetic field, and we're kind of putting the magnetic field in some direction in this SU4 space, and then probing the expectation values of the spin along that direction, and the size of the circles here corresponds to the magnitude of the expectation value. And what you can see is that just looking at the 6x6 cylinder, the expectation values of the SU4 spins in the bulk remain very close to 0. So this is kind of suggesting that there is no long-range magnetic order. And this result is in agreement with also a recent study of the same model done using pseudo-fermion FRG from Cologne. So kind of ruling out magnetic orders in the system, we could again go back to SU2 spins and recall what, understand what were the non-magnetic phases possible there. And a lot of progress was made in that case, starting from the picture of just 2 spins, right, where we know that a pair of spins wants to form a singlet. And this suggests that a possible candidate for the ground state on the lattice could be a covering of the lattice by this singlets. Now, of course, there are lots of different coverings of the lattice, like this or like this. Okay, so you could say that perhaps the actual ground state is a superposition of all of the states, which is, as we know, this is the state of those proposed by Anderson as the candidate ground state for the system. And this is the RVB state, which is a gapped spin liquid. Now, going back to SU4 spins at half filling, we notice that if you have 2 particles per site, then again, if you have 2 sites, so an overall of 4 particles on these 2 sites, they can again form a singlet, which is now an SU4 singlet. They could explicitly write just in the following way, in terms of the states on the 2 sides, where the epsilon is just a full-length symmetric rank 4 tensor. So this suggests that the covering of the lattice by this SU4 singlets now could again be a candidate for the ground state. Now you could ask, why would we expect that this nearest neighbor singlet coverings would actually capture the low energy physics in the SU4 case? We know this is not the case for SU2. But first of all, we know that in the large N limit, if we go to SUN at half filling, due to the theorem Barossa, we know that the ground states are actually described exactly in terms of dimer coverings. But then you could ask whether 4 is already a large enough N. And to get some understanding of that, we could just compare the energies of these 2 representative states of the kind of the classical magnetically like 120-degree ordered state to a single dimer covering of the lattice. So recall that in the case of a 120-degree ordered state, kind of all the bonds, if you look at the side somewhere in the system, all of the bonds are equivalent and they're relatively happy because they're kind of they have an antiferromagnetic component. While in the case of a dimer covering, most of the bonds are unhappy, but then there is one bond on which the dimer lives, and that bond is very happy. So we have to kind of see which configuration eventually wins. And if we look at a triangle lattice and do this comparison for spin 1/2, then the 2 states are actually have the same energy, so it's kind of hard to tell. It would be hard to know which one is a better starting point. But for the case of SU4, if you do the same comparison, we can already see that the dimer coverings have a significantly lower energy than the classical magnetically ordered state. Okay, so this kind of motivates us to do to look at the relevant kind of dimer models or projection onto the dimer space in the SU4 case. And we do this following the procedure by Roxler and Keselman, essentially considering a state, a variational state, which is some superposition of the different nearest neighbor singlet coverings. And one has to remember that when we carry out this the energy minimization in this subspace, one has to remember that the different singlet coverings are actually not orthogonal. Okay, so and this can be seen by just looking at the overlap of these two different coverings of a single blockade, which for the SU4 case is just 1/6. Okay, so this results in this energy minimization procedure giving an not just a standard eigenvalue problem, but a generalized eigenvalue problem, where kind of here on the right-hand side we have this overlap matrix, which exactly captures the overlaps of different singlet coverings. However, this problem can be mapped to a standard eigenvalue problem by defining an effective dimer Hamiltonian, and now my dimers are actually orthogonal. And I can write it formally like this. And however, then when we look at this dimer Hamiltonian, so we can essentially carry out an expansion of this overlap matrix S and the projected Hamiltonian in orders of this parameter X, which is indeed a small parameter in this case. Okay, so carrying out this procedure for the SU4 model, this is the full dimer model we obtain going to up to second orders in X, or equivalently up to loops of length 8. Okay, so we have here basically the kind of the standard dimer in terms of hopping on a plaquette. Then we have kind of hopping along longer loops, and also some mixed terms of hopping depending on the presence of a dimer on the neighboring bond. So to understand what kind of phases this model could host, we could start from kind of the simplest, going to the lowest order, which is like 0th order in X. In that case we remain just with the dimer model, which consists only of hopping on a plaquette. And this model, or actually a slightly more general model, where we also include some potential energy terms, which give some energy to parallel bonds. So this model has been extensively studied, first by Mosner and Sondi, and then more detailed studies were performed by Frederick Wheeler's group. And here we know that for large negative V, for example, potential energy, we expect a columnar phase. For large positive V, we expect the staggered phase where there are no parallel bonds. We know that the point where V over T is 1 is actually an exactly solved point. The ground state is an exact superposition of equal weight superposition of all the different coverings, which is the RK point. And then this extends to a finite region on the phase diagram of where the RVB phase is indeed the ground state. Now in the vicinity of V over T of 0, it turns out that the ground state is a 12-site valence bond state. So it's a valence bond solid with a 12-site unit cell. Okay. Now again, going back to our dimer model with all the additional terms going to higher orders on X, we can do an diagonalization study. And we go up to systems of size 6 by 6, And kind of obtaining the ground states and trying to understand what the ground state is, we look at the bond-bond correlations. So with respect to this bond. And it's kind of hard to see something from the real space picture, but if you do Fourier transform, you can very clearly see two peaks, which exactly correspond to a formation of this 12-site unit cell. So it's kind of hard to say very conclusively based on kind of this system sizes without proper finite size scaling. But at least there is an indication that the ground state in this case also is just a 12-site unit cell. Okay, so to summarize so far, I try to convince you that in the SU4 case, the low energy description we believe could be just in terms of the nearest neighbor singlet coverings, and the projection onto this space and the study of the projected problem suggests that the ground state is an as a 12-site unit cell valence bond solid. But so this, of course, leads to the conjecture that the ground state of the actual SU4 model is a valence bond solid, but this will require further numerical studies, which kind of still remain pretty difficult for this model. So just briefly to mention some effects of SU4 symmetry breaking. So a natural way in which we could SU4 symmetry could be broken in, when we consider a spin on this SU4 coming from the spin and valence degrees of freedom is by adding a Hund's coupling term. And this term would essentially try to pair up the two spins into a spin triplet. So out of the 6 low energy states on each side, out of the six states on each side, will remain only with 3 low energy ones, which correspond to the spin 1, spin triplet and valley singlet states. And then the lowest order in J, what we get is basically a spin 1 Heisenberg model. Now we know that the spin 1 Heisenberg model on the triangle lattice actually orders. Forming a 120-degree ordered state. So we expect that as we increase JH, our system will go from this magnetically disordered into an ordered state. And we can probe this again using DMRG, where this is the result I showed you previously for the SU4 symmetric system where JH is 0. And then this is, as we go to large JH, we can see that a 3 sublattice ordered state indeed forms. And increase in JH gradually, we can see that somewhere around JH of 1, if you look at the expectation value of the spin and the bulk, there is a sharp increase around 1. So this seems like a phase transition into a magnetically ordered state. And we could ask whether there is if the ground state of the SU4 spin model is indeed a valence bond solid for JH equals 0. We could ask whether this is indeed a direct transition from a valence bond ordered state into a magnetically ordered state, and so whether it's a direct transition, and of course, what's the nature of this transition, and whether it could realize a deconfined quantum critical point. So I'd basically like to summarize the half-filled case with those observations, and then I guess I'm running a bit low on time, but so like to continue into the case of quarter filling. So here I'd like to present some evidence for a formation of a gapless quantum liquid. And this is work that was done with the Bauer from Station Q, Tsenke Shu from Curious CSB, and Chaming Jian. Yes, and one thing I would like to mention is that oh, I cannot. Okay, it seems I cannot go back for some reason, but
Hey Anna,
yes.
what is the issue?
Yeah, it seems I cannot go back. I can only go forward again. But okay, so I'll.
Oh, I see.
Yeah, somehow my keyboard is not responding, but I'll try to. I'll try to go forward. Okay, so so to understand the this gapless liquid state, I need to introduce the Parton construction, and this is basically just rewriting the spins, my SU4 spins in terms of the some constrained fermions, which are called the Berkoso fermions, and the statement is that I can just exactly represent my spins in terms of these fermions if I in the following way. If I also introduce the constraint that the number of the fermions of these fermions introduced in each site is exactly 1. Now this there are a few ways of dealing with this constraint. One is by coupling this my Berkoso fermions into an emergent E1 gauge field, and then understanding the results of that coupling. And another way is simply by numerically projecting out all the states in which the occupancy of the fermions is different than 1. And this is called the Gotzwiller projection. So when I actually introduce, rewrite the spins in terms of the fermions, we of course now obtain again, a strongly interacting Hamiltonian in terms of 4 fermion terms. And then you could ask, well, how does this help me solve the problem? But of course, in terms of interacting fermions, what we could do is introduce some mean field decoupling. And a specific mean field decoupling I would like to consider is if we know that this Hamiltonian in terms of spin could be rewritten in terms of the bond operators as just chi dagger chi, where chi is the bond operator corresponding to the helping of a fermion between 2 sites. I could introduce a decoupling in which this chi ij gets a finite expectation value. And I would like to assume a uniform, a state where this chi is just uniform. And this gives me a mean field Hamiltonian where which is simply described by hopping of my of the fermions on the lattice. Now, at the mean field level, the single particle per site constraint just corresponds to some filling of my bands, which you can see here on the right. So the orange shape is really the band structure of my constrained fermions, my Partons, essentially hopping on the lattice, on a triangle lattice, and then the blue circle corresponds to the Fermi surface, which corresponds to a quarter filling. Now this would give rise to, as a many-body state, that would give rise to a Slater determinant state, where you essentially just fill in all the fermionic states up to the Fermi energy. And this is, of course, just some potential state the system could be in, but I would like to claim that comparing to the numerics, we see that this this ansatz reproduces exactly all the main features that we see that we see in the numerics. So, okay, so when we study this system numerically, again using DMRG, we essentially study finite circumference cylinders, And an important point to make here is that when we consider periodic boundary conditions for the spins, this doesn't tell us yet what are the boundary conditions for the partons. Now, in this case, from symmetry constraints, we can say that the partons can have, the fermionic partons can have either periodic or anti-periodic boundary conditions, which essentially would correspond to taking different cuts through the Fermi surface when we look at some finite circumference. Now, the low energy theory description of this quasi one-dimensional systems would be in terms of some one-dimensional bands with some fermionic left and right moving fields. And again, at the mean field level, this bands will just have some resulting Fermi points that come from the filling. But in addition, kind of going again beyond mean field, we would like to understand what are the possible symmetry allowed perturbations to this state. And it turns out that for the case of widths 2 and 4 cylinders, there is an allowed Umklapp scattering, which is relevant in the RG sense, just because the distance between the Fermi points turns out to be pi. So so one could write a relevant Umklapp scattering term. Now, such a perturbation would break translation symmetry and open a gap in the system. And this is indeed what we see in our DMRG results for widths 2 and 4 cylinders. So looking at the spin gap, we see that it's finite, and also looking at the bond expectation values, we see a pattern which breaks translation invariance. And this, in both of these cases, these are just the kind of the middle 4 rungs out of a larger cylinder. And you can see that also in the middle of the cylinder, and there is a clear two-side unit cell which is formed, which is consistent with the field theory prediction. Now, in the case of 3-leg cylinder, we see that we don't expect any relevant Umklapp perturbations, and what we see numerically is that the state is indeed gapless. So here the blue dots are the actual data points as you increase the size of the system. And the different dashed lines are just different fits, either allowing for a finite intercept or not. And you could see that they're both roughly consistent with the data, suggesting again that the state is indeed gapless. Now, trying to understand the nature of this gapless state, we can look at the structure factor, so just this fortress of the spin-spin correlation, and compare it to the ansatz we have from the mean field. So here on the left, you see the DMRG result for the structure factor, and the different curves here correspond to different transverse momentum. And on the right, you can see that structure factor you would expect from the mean field ansatz I showed you before. So simply uniform hopping on a triangular lattice using antiperiodic boundary conditions. And you can see that kind of all the main features, the cusps and the structure factor, show up at exactly the same points, and this points exactly corresponds to the 2 kFs of the Fermi surface. Now, going kind of beyond mean field and implementing the Gutzwiller projection, so kind of the Parton constraint, we see that all the main features remain. So like the 2 kFs remain, the cusps remain at the same momentum. Okay, and this is basically an analysis which is similar to the one carried out by Matthew Fisher and the company for the case of SU2 spins with a ring exchange term, where it was also claimed that that the ground state is indeed a spin on Fermi surface. Okay, so just to summarize, I would I tried to show that the numerical DMRG results that we have on finite circumference cylinders for this quarter filling case are consistent with the mean field ansatz of just a uniform hopping on a triangle lattice. If we also take into account the symmetry allowed perturbations. Now in the limit, there is no Fermi surface nesting, so we expect this phase to be stable and remain gapless. And of course, if we wanted to include SU4 symmetry breaking perturbations, so we would expect that small perturbations would only the Fermi surfaces, but of course, more detailed and further numerical analysis is required to establish that. Okay, so I wanted to show you that in presence of kind of larger local continuous symmetries, or when the local degrees of freedom have a larger symmetry, we can have a variety of interesting phases appearing in a very simple model, basically just of nearest neighbor coupled spins on a lattice. Thank you.
All right, so we are running short a little bit on time. So we have time for one quick question or two at most. All right. If there is no question, thank you so much, Anna. So we're gonna move on to the next speaker.